Welcome to lecture 6 of this course Linear Algebra for AI and ML. Today we'll introduce the concepts of linear independence, linear dependence of vectors. So let's start with the definition of linear dependence of vectors. Linear dependence. So let x1, x2 up to xk be a collection of k vectors in n-dimensional Euclidean space Rn. This collection of vectors is called as linearly dependent. Collection, or more loosely, the vectors are called as linearly dependent. The vectors are called as linearly dependent if beta 1 x1 plus beta 2 x2 plus beta k xk, there are k vectors in the collection we have considered, beta k xk is equal to 0 holds for some beta 1, beta 2 up to beta k scalars not all equal to 0, not all equal to 0. So this last bit is a really important bit, not all equal to 0. So if you notice, the linear combination of vectors x1, x2 up to xk is considered, and if you take beta 1 equal to beta 2 equal to beta k equal to 0, then this linear combination is always going to go to 0. But what is linear dependence of the vectors x1, x2 up to xk demanding? It is demanding that there exists a non-trivial linear combination of vectors which is actually equal to 0. So 0 vector is a linear combination, non-trivial linear combination of these vectors x1, x2 up to xk. This is a very interesting property, and we will explore it little bit further. So not all equal to 0 is going to play a really crucial role. So let x1 up to xk in Rn be linearly dependent. If that is the case, then beta 1 x1 plus beta 2 x2 plus, so I will write it down in a little bit different way than the one that I have written here. This implies there exist scalars beta 1 up to beta k in R, not all 0, such that beta 1 x1 plus beta k xk is equal to 0. So let us consider that let beta j be not equal to 0. Okay, so let us consider the jth not, they are all not 0, so at least one of them is not equal to 0. So let us consider beta j, and then what does this mean? That means that I can write down xj as minus beta 1 by beta j x1 minus so on so forth minus beta j minus 1 by beta j xj minus 1 minus beta j plus 1 by beta j xj plus 1 minus so on so forth beta k by beta j xk. So what does that mean? That means that I can write down at least one vector in this collection, in this particular case xj, as linear combination of the remaining vectors. So linear dependence of x1 up to xk implies that at least one vector say xj is a linear combination of remaining vectors. So that's why this term linear dependence comes into the picture. What it really means? It means that one vector in the collection is dependent on the other vectors. It can be deduced from the other vectors in a linear fashion by taking linear combination. That's why this term linear dependence of vectors comes into the picture. Conversely, let x1 up to xk be a collection of vectors. Let this be a collection of vectors such that one of them is a linear combination of the remaining vectors. Okay, so let us say xj is some linear combination alpha 1 x1 plus so on and so forth, alpha j minus 1 xj minus 1 plus alpha j plus 1 xj plus 1 plus so on and so forth, alpha k xk. That's the linear combination. That's the way it depends. So this implies that alpha 1 x1 plus so on so forth, alpha j minus 1 xj minus 1 plus 1 times xj plus alpha j plus 1 xj plus 1 plus so on so forth, alpha k xk is equal to 0. Correct? So there is a non-trivial linear combination of vectors x1, x2 up to xk which is actually equal to 0. You know for sure that there is at least one alpha i's which is not equal to 0, namely the jth one, alpha j. So this implies that x1 up to xk are linearly dependent. So linear dependence is actually equivalent to this fact that one vector is actually linear combination of the remaining vectors. So that is something that is a useful thing, and that actually is the defining thing of linear dependence. In particular, this is interesting. In particular, let k is equal to 2, then x1, x2 linearly dependent implies that one is the multiple of the other, right? One is the multiple of the other. So when you get two vectors which are linearly dependent, they have to lie along the same line, right? So in particular, in this particular case R2, this vector and the other vector is just scaled version of this vector. So this red one and black one, they are linearly dependent because I can write down red one as, say, for example, red is equal to, say, maybe 2 times black, right? So red is equal to 2 times black. So one is the linear multiple of the other. In other words, geometrically, what has happened? Geometrically, they are lying on the same line, this green line which I have drawn. So that's what linear dependence really means. And what is the converse of this statement? The converse of this statement is that if the two vectors does not lie, if the two vectors in R2 do not lie on the same line, what happens? You cannot write one vector as linear multiple of the other. So the two vectors which do not lie on the same line in R2 are not linearly dependent. Such vectors we will call linearly independent vectors. Okay, so let's write down the definition of linearly independent vectors. Linearly independent vectors. So a collection x1 up to xk in Rn is called as linearly independent if it is not linearly dependent. Okay, so this is a definition which does not give you much information, but from the definition of linear dependence, what do we mean? We mean that this implies that if you see beta 1 x1 plus beta k xk is equal to 0, then what is the choice for the values of beta 1 up to beta k? Then that means that beta 1 has to be equal to 0 and has to be equal to beta k. So all these k scalars have to be equal to 0, because even if one of them is not equal to 0, what you really are saying is that there exists a non-trivial linear combination of these vectors x1, x2, xk, which is actually equal to 0. So 0 is actually a non-trivial linear combination of these vectors. That is not possible because the vectors are not linearly dependent. That means that the only choice that is left for the scalars to be is actually equal to 0. So if these scalars are equal to 0, then you will call that this collection is linearly independent, which is same as saying that if it is not linearly dependent, then it's linearly independent. So in general, you have to understand, in general, it is difficult to check if a given collection is linearly dependent or not. But we will see a few simple examples where we will be able to verify quickly that the set is so a collection consisting of one vector. So I will not write one like this, consisting of a single vector is always linearly independent if and only if the vector is non-zero. So what is this statement? This statement is really interesting statement to look at. So x1 belonging to Rn. So if x1 is not equal to 0, then what is the linear combination that you are looking at? The linear combination that you are looking at is beta 1 x1 is equal to 0 will always imply that beta 1 has to be equal to 0, because otherwise this equality cannot hold true, which means that x1 is linearly independent. But if x1 is a 0 vector, then you can choose any non-zero scalar. Say beta is equal to 1, you can choose all ones, the vector beta is equal to 1, the scalar 1. Then for all the entries of x1 are 0, then any number into that 0 vector is still going to get you a 0. So if it is a 0 vector, then it is linearly dependent, but if it is not 0 vector, then it is linearly independent. So this is a fun thing, and we will use this fun thing in our next example immediately, that any collection of vectors including 0 vector, including the 0 vector, is always linearly dependent. And now you know why this is going to happen, because what you do, you have a 0 vector in the collection, so you multiply that 0 by 1, so 1 into 0, that is 0, and you take all other scalars x1, x2, xk, all other scalars corresponding to x1, x2, xk to be equal to 0. So you have 1 into 0 plus 0 into x1 plus 0 into x2 plus 0 into xk, and this is always going to give you 0. And this linear combination is a non-trivial linear combination, because at least one scalar is not equal to 0. So you see, the definition is termed very nicely it says that at least one should be not equal to 0. So, you are allowing 0 vector to be part of the collection, and if the 0 vector is part of the collection, then it will always be linearly dependent set. Another example is, you have been seeing it from first lecture and you must have guessed it by now. You took E1, E2 up to Ek in Rn. Okay, maybe you can go all the way up to n, it doesn't matter. E1, E2 up to En, unit vectors, okay, are linearly independent. Why unit vectors are linearly independent? Because you consider this linear combination beta 1 E1 plus beta n En is equal to 0. What does that mean? That means that you are looking at the vector beta 1 beta 2 up to beta n is equal to 0 0 0, correct? Which implies that all the beta i's are equal to 0 for every I. So, you look at any linear combination of the unit vectors E1 E2 up to En, and if that linear combination happens to be equal to 0, then you are sure that that has to be the trivial linear combination. That proves that these vectors are linearly independent vectors. Okay, so E1, E2, En, collection of unit vectors is linearly independent. Now, you consider this collection 1 0 0, okay, then 0 minus 1 1, and the third vector is minus 1 1 1, okay. So, this is the collection that you have, and you want to check whether this collection is linearly independent or not. So, let us start with the linear combination. So, you have beta 1 into 1 0 0 plus beta 2 into 0 minus 1 0 plus beta 3 minus 1 1 1 is actually equal to 0 0 0. That is the linear combination that I am taking. So, I will say consider this. Then what do we want to show? We want to show that all the beta i's are equal to 0. If you can show that, then you will show that this collection is linearly independent. Otherwise, it is linearly dependent, right? Linearly independent or not? That is the question we are asking. So, what will this imply? This implies that beta 1 minus beta 3, then you have minus beta 2 plus beta 3, and you have beta 3, correct? So, these are all equal to 0 0 0, but this means that beta 3 is equal to 0, and I substitute back this, which further implies that beta 1 is equal to beta 2 is equal to 0. That means that if you look at this linear combination, then it has to be the trivial linear combination. That means that these vectors are linearly independent. But now you see, this may not be always easy. These vectors, the entries in the vectors are chosen in such a way that I can very easily and quickly illustrate whether these vectors are linearly dependent or not. Okay, but every time in real life, it may not be as easy as this particular example to check whether the vectors are linearly independent or not. Okay, so this is about few examples. So, let us talk about linear combination of linearly independent vectors. Okay. So, these linear combinations of linearly independent vectors are really very interesting thing. These are the things we will use extensively in this course, and if we understand this concept of linear combinations of linearly independent vectors very well, then we will know all the things that we want to understand about the solution of system of linear equations. So, little later in this lecture possibly I am going to relate this to solving system of linear equations. I will tell you how, but let us try to understand this first. Okay. So, let y in Rn is a linear combination of x1 up to xk in Rn, which are linearly independent. Okay. So x1, x2, xk is a collection of linearly independent vectors, and we are saying that y in Rn is a linear combination of these x1, x2 up to xk. So y is a linear combination of this x1, x2 up to xk. That means that y is equal to some beta 1 x1 plus beta 2 x2 plus beta k xk. That's what I know about this vector y. Okay, now what I claim is that the coefficients in the linear combination are unique. So what does that mean? That means that y can be uniquely expressed as linear combination of these linearly independent vectors x1, x2, xk. The uniqueness is coming because of linear independence of vectors x1, x2 up to xk. That is really very important. Okay, so how to prove that? In order to prove this claim, we will use contradiction. So on contrary, assume that there exists another linear combination, another set of scalars gamma 1 up to gamma k in R such that y is actually gamma 1 x1 plus so on so forth plus gamma k xk, correct? So I'll call this equation as equation 2, I will call this equation as equation 1. Then what will I do? I'll do 1 minus 2, 2 minus 1, whatever you want to do. What do you get? You get beta 1 minus gamma 1 into x1 plus so on so forth, beta k minus gamma k into xk is equal to 0. So now what do you have? You have a linear combination of linearly independent vectors, and that linear combination is equal to 0. What does that mean? That means that the coefficients in that linear combination must be equal to 0 identically, which means that beta 1 minus gamma 1 has to be equal to beta 2 minus gamma 2. All of them have to be equal to 0 because of linear independence of vectors x1, x2 up to xk, which basically means that gamma I has to be equal to beta I for I is equal to 1 to up to k. And that really means that given a collection of linearly independent vectors x1, x2 up to xk, if you can write a vector y as linear combination of these vectors x1, x2 up to xk, then that linear combination is unique. There is no other linear combination that will give you the same value. Okay, so that is something that is interesting, and why that will fail for linearly dependent vectors, let's try to understand. So why? So this is sort of proof complete for the claim. Why does this not hold true for linearly dependent set? Linearly dependent. Okay, so I will try to give the idea for two vectors. You can think of it for many vectors. Okay, so suppose x1 and x2 are in Rn linearly dependent. Okay, if they are linearly dependent, then there exists k. Okay, so k is the index I am using. So there exists some beta not equal to 0 such that x1 is equal to beta x2, right? One vector has to be a multiple of other vector in order that the two vectors are linearly dependent. So there exists beta such that this thing happens to. Now let y be a linear combination of these vectors. So alpha 1 x1 plus alpha 2 x2. Correct? So y is basically this. So now what is going to happen? We want to see whether these alpha 1 and alpha 2 are unique or not. But this alpha 1 and alpha 2 need not be unique. Why? Because you can write this alpha 1 x1 plus alpha 2 x2. You can substitute for x1. So you get alpha 1 beta x2 plus alpha 2 x2. So this is basically alpha 1 beta plus alpha 2 into x2. So y obviously has to lie on the line, because it's also a linear combination of two vectors which are lying on the line. And now you can scale these x alpha 1 and alpha 2 in any way whichever, and you still will lie on that particular line. You will still get that particular vector y, right. So that is something that is very clear from this equation. So for two vectors it is straightforward to see that there will be multiple choices of alpha 1 and alpha 2 in order to get to the vector y. You just have to play around with those choices. So that is something that is important. So how do you do that? Let me say it clearly. So this number, let us call gamma. So if this number is gamma, then you know that y is equal to gamma times x2, right. That's something that you know. And gamma is what value? Gamma is alpha 1 beta plus alpha 2. And now you are free to choose any values of alpha 1 and alpha 2. So alpha 1 and alpha 2. So now there exist infinite choices of alpha 1 and alpha 2 such that gamma is equal to alpha 1. Okay, so maybe I will not use alpha 1 and alpha 2. Let's use delta 1 and delta 2, and if you use those choices delta 1 and delta 2, then there exist infinite choices of delta 1 and delta 2 such that this is true. Gamma is equal to delta 1 beta plus delta 2. Okay, and using this delta 1 and delta 2 you can adjust your alpha 1 and alpha 2 always. So that is something that you can always do, and based on that you can show that this will not be true for linearly dependent set. So that is something that you have to understand. So another important note that you have to understand is that any superset of collection of linearly dependent vectors is linearly dependent. Correct. So you add some vectors to a given linearly dependent set. So when you add vectors to the given linearly dependent set, whatever vectors you have added, you multiply those vectors by 0 0 0, right. So you already had a linearly dependent collection, so there was a non-trivial linear combination which was going to 0, and now you add some more vectors and multiply them by 0, then the superset collection will always have the same linear combination of the original vectors plus 0 0 0, and you will get the 0 vector. So this superset of any collection of linearly dependent vectors is going to be linearly dependent, and if that is true, then you look at the equivalent statement for linearly independent set. What is that? Any non-empty subset of any non-empty subset of linearly independent vectors is linearly independent. Okay, so this is equally easy to prove. So these two statements, I think you think about them and make sure that you understand completely, because this is a very important concept that we will use now subsequently. Okay, so now we define, so now I want you to observe one important inequality. Okay, so that thing, independence dimension inequality. Okay, independence dimension inequality. What is this independence dimension inequality saying? If x1 up to xk in Rn are linearly independent, then k has to be less than or equal to n. So, what is k? K is how many number of vectors are there in the collection, and n is what is the size, what is the length of the vectors that you are talking of. So, there is an upper bound on the number of vectors that you can have in the collection of linearly independent set. You cannot have an arbitrarily large linearly independent set. Remember, you can have an arbitrarily large, arbitrarily big in cardinality linearly dependent set, because if you find one linearly dependent set, you can add as many vectors as you want to add to that linearly dependent set, and it will still continue to be linearly dependent. So, the cardinality of linearly dependent set, there is no bound, absolutely no bound, but linearly independent set, there is a cardinality bound. What it says? If you have a linearly independent collection, then that collection cannot have more than n number of vectors in it. And where is that n coming from? That n is coming from the size, the length of the vector. Okay. So, this is a very important fact, and this fact actually enables us to define something which is called as basis, okay, and dimension of a vector space. Okay. So, we will come to those definitions after we prove this statement. And what is what is equivalent of this statement? Okay, what is equivalent of this statement? This statement is same as saying that any collection with n plus 1 vectors from Rn is linearly dependent. So, this is very interesting. You collect any n plus 1 vectors. So, it is a profound statement you are making, right? You collect arbitrarily any n plus 1 vectors in Rn, that set is bound to be linearly dependent set. So, let us try to understand this in R2, the space which we are very familiar with. So, in R2 what are we saying? In R2 we are saying that you take any 3 vectors. You collect any 3 vectors which are randomly collected, and you will see that those 3 vectors are actually linearly dependent. What does that mean? That means that you can write one of them as linear combination of the other 2, right. So, what do? You have one vector here, you have one vector here, you have one vector here. So, suppose this vector is, this vector is x1, this vector is x3, and this vector is x2. Suppose you take this as your vectors x1, x2, x3, then what happens? What you can do is you can scale this vector x1. So, I have drawn the diagram in such a way that I can draw a parallel vector here, and that vector will basically be gamma 1 into x1 for some gamma 1, and this vector x2 is with scaling 1 only. So, 1 times x2 plus gamma 1 x1 will actually be equal to x3. So, I have a linear combination. Where I am writing one vector x3 as linear combination of these 2 vectors x1 and x2. So, I can do that, and now I can do anything. So, suppose these vectors I have drawn in such a way. So, this vector x1 can be x2 can be in a smaller magnitude. So, in order to complete a parallelogram I can do this. So, I take 2 vectors x1 x2, I try to make it into 2 sides of the parallelogram such that the third vector x3 becomes its the third vector x3 becomes its diagonal, right. So, here I had to scale this vector x1 down by gamma. So, I had that vector gamma 1 x1, and I have this vector x2. So, gamma 1 x1 and x2, their addition will actually be equal to x3. So, geometrically this is very clear in R2 plane that any 3 vectors you see, you can always write one vector as linear combination of the remaining 2 vectors, and hence the collection of those 3 vectors in R2 will always be linearly dependent. If one of them happens to be 0 vector, then job is even easier, right. One of them is 0 vector. We have already seen that any collection with 0 vector is going to be linearly dependent set. So, job is easy. So, this inequality is very important. So, what is this inequality saying? This inequality is saying that if you have collection of k vectors in Rn which are linearly independent, then that collection cannot exceed, the number of vectors in that collection cannot exceed n. Put another way, same statement, what it really means? It means that if you have a collection of n plus 1 vectors in Rn, then that has to be a linearly dependent collection of vectors. So, we will try to prove this inequality first. So this proof is very interesting, and proof is based on the fact which is called as mathematical induction. So what happens in mathematical induction? So in mathematical induction, you assume something. What do you assume? You assume the base case. You prove that for n is equal to 1, this is true. Then you assume it for n minus 1, and then you try to prove it for n using n minus 1. That's the induction principle. So if you can do it for any arbitrary n, then you are actually proving what you really want to prove. So what is the base case? The base case is when n is equal to 1. Okay, so consider the base case. Base case n is equal to 1. So in n is equal to 1, what is the hypothesis? Hypothesis is that x1 up to xk belonging to R1, meaning basically R is a linearly independent collection, right? That is given to us. This linearly independent collection is given to us. Once we know that this is linearly independent collection, at least one of the, so the vectors have to be not equal to 0, because if one vector is 0, then you have linearly dependent collection. So x1 is not equal to 0. Once x1 is not equal to 0, then you can write down x2 as minus you can write down x2 as minus x2 by x1 into x1. Am I right? This is what you can write. And similarly x3 you can write, there is no need of minus n, sorry. x3 you can write as x3 divided by x1 into x1, and so on and so forth. xk as xk by x1 into x1. So this is the scalar, this is the scalar. So you are writing x2 as gamma 2 x1, x3 as gamma 3 x1, so on and so forth, xk as gamma k x1. So basically all the other vectors are linear multiples of x1. That means that x1, x2 up to xk becomes a linearly dependent collection. But what is the assumption? The hypothesis is that x1, x2, xk is linearly independent collection. So this implies that so this means that k has to be less than or equal to 1, which means that k has to be equal to 1. That means that linearly independent collection, if you have, then the only possible way you can have linearly independent collection in R1 is of one non-zero vector, that's it. So we have proven this for base case, that k has to be less than or equal to n, right? So now we suppose n is greater than or equal to 2, right? So let this be greater than or equal to 2, and let us assume that it holds for dimension n minus 1. Okay, so assumption is that this inequality, what we call this inequality, independence dimension inequality, holds true for n minus 1. Okay, so it holds true for n minus 1. So what does that mean? It means that given a collection of k vectors, so let x1 up to xk be a collection given to us. Okay, and this collection is, okay, so let me not say this, but if you are given a collection of k vectors in n minus 1, then that k has to be less than or equal to n minus 1. That's the meaning of the assumption, right? And now what do we want to do? We want to prove that it holds true for n, right? So what do we want to say? So let x1, x2 up to xk be a collection of linearly independent, right? This is what we have. So this x1, x2 up to xk in Rn be linearly independent. Then we want to prove k is less than or equal to n. That's the objective. We should be able to prove this for k less than or equal to n. And what is the only thing that we are allowed to use here? We are allowed to use the only fact. What is the fact? That this holds true for n minus 1, meaning okay, so this holds true for n minus 1. So assume that this independence dimension inequality holds true for n minus 1. So what are we? So what is it that we want to prove? Given a collection of k vectors in Rn which are linearly independent, we want to show that k is less than or equal to n. And what are we allowed to use? We are allowed to use the fact that if you are given a k collection of vectors in an n minus 1 dimensional space, then k is less than or equal to n minus 1. That is what you are allowed to use. Okay, so we will try to use that to prove this particular fact. Okay, so what are we going to do? We are going to do a very interesting thing. So I will write down this xi as yi into alpha I belonging to Rn for I is equal to 1 to up to k. So what I have done is I have written this vector xi in a block notation where these yi belong to Rn minus 1. So I have an n minus 1 block, and alpha I, the last entry, is a scalar entry, right? So what are the possibilities? So first, case 1. What is the case 1? Alpha I equal to 0 for I is equal to 1 to up to k. Alpha is equal to 0 for I equal to 1 to up to k. That is one possibility, that all the alpha i's, all the scalars in that block thing, all the last entries of xi is equal to 0, or at least one of the entries in xi is, the last entry is not equal to 0. These are the two possible cases. We are looking at the first possible case, that all the entries alpha is equal to 0. So if that happens, then what will happen? Then this b1, b2, bk, we will see what holds true. Okay, so this is linearly independent, that is given to us, right? So since x1 up to xk is linearly independent set in Rn, beta 1 x1 plus beta k xk is equal to 0. What will that imply? That will imply that beta 1 y1 plus beta k yk also is equal to 0, because all the alpha is are equal to 0, right? So I will just remove this thing. So this is a vector equation in, so these are n vectors, right? I hope you understand. These are n vectors and these are n minus 1 vectors. I am just dropping the last entry because those last entries are anyway equal to 0. So it doesn't matter if I drop them. So this 0, the first equation, this 0 actually is in Rn, while this 0 is in Rn minus 1. I hope you understand this. But this is equal to 0. So what can you say? All the beta i's are equal to 0 because x1, x2, xk is linearly independent. This implies that beta 1 equal to beta k is equal to 0. But this equation, the second equation here, is telling us that because beta 1 equal to beta k is equal to 0, y1 up to yk also is linearly independent in Rn minus 1. And if that is true, then k has to be less than or equal to n minus 1. This implies k has to be less than or equal to n minus 1 because of this assumption that we have made, because of this assumption star that we have made. And if k is less than or equal to n minus 1, clearly k is less than n. So what we really wanted to prove, k has to be less than or equal to n. If all the alpha is 0, then k is actually strictly less than n. Okay, so that part is proved. So now we have to look at the second case. What is the second case? The second case is that at least one of alpha i's is not equal to 0. Okay, that is what we have. So if let us assume that alpha j is not equal to 0 for some j between between 1 to up to k. Okay, so there is at least one alpha j which is not equal to 0. Then what do? I define new vectors zi which are given as bi minus alpha I divided by alpha j into bj. So the index will run from I equal to j minus 1, and I will define zi to be bi plus 1 minus alpha I plus 1 divided by alpha j bj when index I is equal to j up to k minus 1. So that is how I will define these new k minus 1 vectors. Okay, so these are the collection of new k minus 1 vectors that I have, and I will prove that these k minus 1 vectors are linearly independent. Okay, so these k minus 1 vectors are linearly independent. What will that help me prove? That will help me prove that k has to be less than or equal to n. So claim zi I is equal to 1 to up to k minus 1 are linearly independent. Okay. So if they are linearly independent, what are you going to do? Summation bi zi I from 1 to k minus 1 is equal to 0. Then I will expand this, right? bi zi equal to 0. I will expand this. So if I expand this, what do I get? I can split the summation between two parts, one up to j minus 1, and the one where I have j minus 1, I have this yi alpha I, correct, plus gamma yj alpha j plus summation I from j plus 1 to k, and I have beta I minus 1 yi alpha I is equal to 0. So again you have to understand that this equation is n minus 1 dimension equation, okay, in Rn minus 1, but this equation is in n dimension. And what is the value of gamma? The value of gamma is minus 1 upon alpha j into summation beta I alpha I from 1 to j minus 1 plus I from j plus 1 to k beta I minus 1 alpha I. So this is a little bit technical, but you have to understand this proof. Okay, so this is the expression for gamma I, and because this set is linearly independent, so what will happen? You will have k minus 1 less than or equal to n minus 1, right? So k minus 1 is less than or equal to n minus 1, which will imply that k is less than or equal to n. So this proves the theorem, right? So now that I have this inequality in place, now I can define important things such as basis. So what is a basis? The definition of basis. So collection of n linearly independent vectors in Rn is called as basis. So now from this independence dimension inequality, now you can see that this basis basically is a maximal independent set. So you are collecting the collection which can be maximally independent. If you add any more vector to it, it will become linearly dependent. Just at that stage, what do you have? That is the linearly independent set. Okay, so that's actually called the basis. And once you know this is the basis, your job is done. The number n is called as dimension. Okay, so that's the dimension. So what is the maximal independent set that you can find out in a vector space? That's what you are looking for. In this particular case of n dimensional Euclidean space, that number is n. If you have collection of n plus 1 vectors, that's linearly dependent. That's what we saw earlier. So this number n is a unique number, so that is called as dimension. Please remember that there can be more than one basis. In fact, there are infinitely many bases in Rn. There are infinitely many collections of independent vectors, but what is independent, what is unique amongst all of them? The number that is unique, the number that is invariant is the dimension. So you can have different independent vectors collected together to form a basis, but what will not change is how many of them are there in that set to form a basis. That's n, right? So that is why this number n is invariant. It's important, it's called as dimension. So any vector, okay, so I will say let x1 up to xn be a basis of Rn. Okay, so this is a collection of linearly independent sets, linearly independent vectors in Rn. Because that collection has n entries, it will be a basis of Rn. I am specifically using the word a basis of Rn because there can be more than one basis. Okay, so so we'll see. So let this be a basis of Rn. If that is true, then any vector y in Rn can be uniquely expressed as a linear combination of vectors in x1, x2 up to xn. Why is that true? By this independence dimension inequality, what do you know? You know that this collection x1, x2, xn and y is linearly dependent collection, right? So this collection is linearly dependent. So you can write down y as a linear combination of the remaining vectors. Why can you do that? Okay, so let us write down. So you have beta 1 x1 plus beta 2 x2 plus beta n xn plus beta n plus 1 y is equal to 0. Okay. Here beta n plus 1 cannot be equal to 0. Because if beta n plus 1 is equal to 0, then all the betas will be equal to 0 because x1, x2, xn is a linearly independent set. So you will have a trivial linear combination equal to 0, which will mean that this is a linearly independent set, which is not possible. You have added y, so when you add y, this beta n plus 1 cannot be equal to 0, because if beta n plus 1 is also equal to 0, then beta i's will always be equal to 0, which is a contradiction to the fact that there is a trivial linear combination, only trivial linear combination that will take you to 0. So beta n plus 1 has to be not equal to 0. Once you observe that, so this is the observation. So once you observe that, then you have this y, where you have minus beta 1 by beta n plus 1 x1 minus beta 2 by beta n plus 1 x2, so on and so forth, minus beta n by beta n plus 1 xn. So I have written y as linear combination of this basis element. But what is another property of this basis element? So expressed All right. Why uniquely? Uniquely because x1, x2, xn is a linearly independent set. So, if this is a linearly independent set, and if you are able to write one vector as a linear combination of linearly independent vector, then that linear combination is unique. We have already proved that. So, a vector y in Rn will always be represented uniquely as linear combination of its basis elements. So, that is something that is really very helpful fact, and that fact will help us a lot in understanding solution of system of linear equations. So, this is something sometimes we will use. So, x1 up to xn is a basis of Rn, and y is any vector given in n. Then y can be written as a unique linear combination of these x1 up to xn. So, this is called as expansion of a vector in basis, okay, in basis B. So, that is what you have. Y is equal to alpha 1 x1 plus alpha 2 x2 plus alpha n xn. So, these coefficients are unique. So, sometimes they are also called as coordinates of vector y with respect to the basis B. So, sometimes you write this alpha as this coordinate vector of y with respect to basis B. Okay. So, that is something that is very useful. We will probably make use of this fact later, and these are unique. That is what you have to remember. So, for example, you observe that this set E1 up to En is a basis of Rn, because this is a linearly independent set, and this linearly independent set has already n elements in it. So, it has to be a basis of Rn. Right. So, if it is a basis of Rn, then any vector y in Rn can be written as a linear combination, and you already know what is that linear combination: y1 e1 plus y2 e2 plus yn en, and you look at this y1 up to yn, that actually is the coordinate vector that you wrote here in the first expression, right. So, this is the coordinate vector of y with respect to this basis E1 up to En. So, this basis we will call as canonical basis. Okay, this basis is a very important basis. So, this basis is called as canonical basis Rn. Okay, standard basis, canonical basis. These are the terminologies that we will use to represent this basis. Okay, so what have we done in today's lecture so far? So the summary, what we have done, we defined the concepts of linear dependence and independence. We saw some examples of linearly dependent and independent sets. Then we saw some properties. One of the important properties was independence dimension inequality. Independence dimension inequality. What did this inequality say? This inequality said that if you have a collection of k vectors in Rn which is linearly independent, this implies that k has to be less than or equal to n. And how did we prove that? We proved that using induction argument. Okay. We proved that using induction argument. And once we knew that this is true, what can we say about this inequality? So, this inequality, independence dimension inequality, is same as saying any collection of n plus 1 vectors in Rn is linearly dependent, right. So, that is what this inequality really says. And once we had set this independence dimension inequality, we define the two terms, basis and dimension of Rn, basis and dimension of Rn, and we did something, expansion of vectors in a basis. Right? That's what we did. So these are the important things that we have covered in this lecture. We will continue this discussion in the next class. Thank you.